Okay, so far we've been discussing a little bit modern cosmology. It's a fascinating subject. We can't do it full justice in this course. In fact, it would be nice to have one entire course devoted to that particular subject, because there are many, many things that we don't have time to go into. So we saw that according to the Big Bang theory, the universe started in an explosion where all the matter and space and time were created some 13.7, 14 billion years ago. And it's been expanding ever since. And we looked for the evidence for such an event, and it's the cosmic microwave background radiation. When the universe became transparent to light, some 380,000 years after its creation, the radiation was in equilibrium with matter, and the temperature of the universe at that time was about 3,000 degrees centigrade. It was cool enough so that the protons could capture the electrons and remove the electrons from this dense soup so that the photons could propagate freely among neutral hydrogen atoms. And the universe has been expanding since then. It has expanded roughly by a factor of 1,000. And the wavelength corresponding to that temperature of 3,000 degrees has now increased by the same factor of 1,000 and is now in the microwave range. And the corresponding temperature is about 3 degrees Kelvin. So sometimes people refer to that microwave background radiation as 3-degree background radiation. It was first observed in the 60s by two physicists from Bell Labs, this is Zayas and Wilson. And since then, there were 3 satellite probes launched to examine its details, and certainly inhomogeneities, variations in temperature are detected, but they are still minute. Overall, it's 3-degree background. So that is pretty strong evidence that Big Bang indeed took the place as proposed by the theory. There is another piece of evidence that I didn't discuss because there is no real point, and that is if you apply the laws of nuclear physics to the conditions in that early universe, then you indeed find out that the relative abundance of different chemical elements would be roughly 3/4 hydrogen, 1/4 helium, and small amounts of all other chemical elements. And that's precisely what we see today, right? So there are 2 very strong pieces of evidence: microwave background radiation and the distribution of chemical elements in the universe that fit the scenario of the Big Bang. So then, what is the fate of the universe? What is going to happen? Will it stop expanding? Would the matter in the universe, through its gravitational attraction, hold its expansion, right? Or will it continue to expand forever? And the answer depends on what is the density of matter and energy in the universe. And that density is characterized by a parameter that cosmologists or astrophysicists like to label with the Greek letter omega. And it gives the ratio of the actual density of matter in the universe over so-called critical density. And it turns out that that critical density is 9.5 times 10 to the minus 30 grams per centimeter cubed, which corresponds to about 6 hydrogen atoms per meter cubed, right? So the density corresponds to having about 6 hydrogen atoms in a cube of space, 1 meter on each side. That's pretty low. In fact, our best vacuums on Earth don't provide such low density. Nevertheless, it turns out that that particular number is critical, and what matters is how the actual density of matter in the universe compares to that critical value. So there are different scenarios as to what will happen in the future depending on the value of omega. Okay? If omega is bigger than 1, so if the actual density of the universe is bigger than the critical value, then eventually the universe will stop expanding and it will start contracting. So this set of diagrams illustrates schematically what is happening to the universe. This first flash denotes the creation, the Big Bang, and then the time goes up, and we know that universe is expanding, still is. This particular slice corresponds to the present time, and the size of this disk represents, if you will, the size of the universe, its diameter, right? So if omega is bigger than 1, the universe is expanding now. It will continue expanding. But then the gravitational force of matter in the universe will halt that expansion, right? Just as when you throw something in the air, the Earth's gravity will slow it down and eventually force it to come back to Earth. So if omega is bigger than 1, then the universe will stop expanding at some time in the future, and it will start contracting, and it would end in what is called Big Crunch. Right? It was created in the Big Bang, and it would end in a Big Crunch if omega is bigger than 1. But it turns out that that value of omega also has implications on the global curvature of space. I'm not talking about the local curvature of space, such as increased curvature near a star like our sun. We saw that the sun's mass is such that it's sufficient to bend the space around it so that it bends the starlight from the distant stars that pass near it. I'm not talking about that curvature that is caused by a local distribution of mass in the universe, right? You have the same positive curvature, or rather curved space near a black hole or a neutron star. I'm talking about the global, overall curvature of the universe, okay? So if omega is bigger than 1, the universe has a positive curvature. It's hard for us to imagine, to see a curvature of our space, right? Because we developed in a three-dimensional space, our nervous system developed in three-dimensional space, so we have hard time visualizing things in higher dimensions. But we can get an idea as to what is involved by looking at lower dimensional space. Then we can appreciate the idea of different types of curvatures. So positive curvature is just like the curvature of two-dimensional surface of a ball, right? Here you have a tennis ball, right? And it has a positive curvature, and there are several different things associated with positive curvature. If you had two lines that were locally parallel to each other, like if these two bugs, when they started crawling, they were moving in parallel directions, it could happen that actually these lines would eventually cross, that these two bugs would at some point be at the same spot, okay? So that is the feature of a space with a positive curvature. So if this was the case, right, then if I had here a massive object, say a black hole or a neutron star or a star, right, it would make a local indentation, right, around that particular object. But globally, overall, the universe would have positive curvature, just like the two-dimensional surface of the ball. If omega was less than 1, then we would have universe expanding forever at a constant rate. This type of expansion is referred to often as the coasting universe, okay? And if this was the case, if omega was less than 1, then the universe will simply continue expanding. There is not enough mass, there is not enough matter in the universe to halt that expansion. And it turns out that in that case, if omega is less than 1, that the overall, the global curvature of space-time would be negative. So if omega is less than 1, we have this so-called coasting universe. It keeps on expanding at a constant rate, but the curvature, the global curvature of the space-time is negative, just like the surface of a saddle. So in the case of space with negative curvature, unlike the space with positive curvature, if I had two lines that were initially parallel to each other, if these two bugs were initially moving in the same direction, in the space with negative curvature, these two initially parallel lines could actually diverge from each other. These two bugs would be moving at increasing distance, so that the distance between them is increasing, okay? So that's the feature of a negative curvature of the space-time. And finally, if omega was equal to 1, which is this middle panel here, the universe will continue expanding, but the rate of expansion would slowly decrease in time and eventually become 0 in infinite future, okay? And in infinitely distant future, that expansion would stop, okay? So after the Big Bang, the universe is expanding and always will be expanding, but the rate of the expansion, as indicated by the slope of this line, is slowly decreasing. It will always expand, but the rate at which it expands, it would be slowly decreasing and it would become 0 at infinite future. So if omega was equal to 1, we would have a so-called critical universe, and the global curvature of space-time would be 0. The space-time would be flat, okay? So here is a familiar case of zero curvature. Actually, our everyday experience tells us that we live in such space, right? Euclidean geometry is actually, there are certain postulates of Euclidean geometry that are intuitively clear because they are so close to our experience. And in this space with zero curvature, two lines that were parallel initially will always stay parallel to each other. They would never intersect or diverge from each other. These two bugs would always be at the same distance from one another, okay? One of the Euclidean postulates is that basically two lines that were parallel at a particular region of space will always remain parallel. Right? So if omega happens to be exactly equal to 1, the universe would keep on expanding, but the expansion rate would slowly decrease to become 0 not in any finite interval of time, but at infinite future. So what are the observations? Well, there was a spectacular discovery in late 90s by two groups of astronomers. They used type 1a supernovae to measure the distances to the most distant galaxies in the universe. Because of the reasons we discussed before, they are very bright, therefore they can be seen from large distances. They always have the same luminosity because the mechanism is always the same. So we can calibrate their luminosity. So what they found is that about 4 to 5 billion years ago, the rate of expansion started to increase. Okay, so this is not quite accurate, this description. Basically, this sudden increase in rate started some 4 to 5 billion years in the past. Okay, but you get the picture. What was observed is that as of 4 to 5 billion years ago, the rate at which the universe is expanding is increasing. The expansion is accelerating. And for that discovery, which was fundamental, it completely changed our understanding or our picture of our entire universe. They were awarded the Nobel Prize in Physics in 2011. So the question is why? What caused it? And of course, we physicists and astrophysicists are very resourceful. We always have, there is some new experimental measurement, something earth-shattering, and there is bound to be somebody on the Earth who already has an idea as to what is happening. So what people did, and that was the simplest thing to do, is to reintroduce so-called cosmological constant, which was introduced by Einstein after he formulated his general theory of relativity. And the reason he introduced it, because general theory of relativity predicted, among other things, the possibility that the universe could be expanding. Okay? And in 1916-17, there was no observational evidence for that. All observations pointed out to the steady state universe, where the universe is neither contracting nor expanding. So Einstein, in order to prevent the universe, and basically at that time, the universe was largely restricted to our own galaxy, he introduced by fiat, by hand, an additional term that was not there initially in his equations of general relativity. And the effect of that term that he called cosmological constant was actually to counteract the gravity, right? Because if without that term, Einstein's equations would say that all the mass in the universe would cause it to collapse. And it wasn't collapsing. The observational evidence at that time was that it was neither expanding or contracting, right? It was in that sort of steady state. So to reproduce that observation, he introduced an additional, totally artificially, without any deep reasons, such as symmetry. You know, usually we in physics use symmetry arguments as most fundamental principles in setting up a theory, because we believe that the universe is symmetric, beautiful, right? So he introduced this so-called cosmological constant to prevent the collapse of the universe under its own gravity, right? So the astrophysicists then said, once they discovered that the expansion is accelerating, that, if we had in Einstein's equations this term, again, that is counteracting gravity, we can explain, albeit phenomenologically, the expansion of the universe. Okay? And why did Einstein said later that that was the greatest blunder of his career was, of course, the observations by Hubble in 1929 were consistent, as we discussed in great detail before, with an expanding universe. So the universe wasn't static, it was actually expanding. That was clear after Hubble's observations. Okay? That's why Einstein called it the biggest blunder of his career. But that cosmological constant is now again invoked in order to explain that there is something that is counteracting gravity and actually causing the expansion to accelerate. So basically, this is very qualitative explanation, but I hope you will get the idea. Suppose that we have a bunch of galaxies, 3 here, right? And they are attracting each other with the force of gravitational attraction, as I've indicated with these yellow arrows, right? Each 2 galaxies are attracting each other. This one here is pulling on this one to the left with the force of gravity, and at the same time, the one on the left is pulling on the galaxy on the right with equal force, but opposite direction. And of course, the same with these 2 and these 2. They're attracting each other, right? These forces of gravity are trying to pull them together. And gravity caused by mass and energy, as we know, it decreases with distance, right? Not only in Newtonian theory of gravity, but also the same is true in the general theory of relativity. On the other hand, this cosmological constant is the property of space-time itself. It has no relationship to the matter in the universe, okay? And it is counteracting the gravity. It's trying to pull the galaxies away from each other. Moreover, unlike gravity that decreases with distance between the 2 objects, it acts over all distances. It's totally distance independent. So then the idea is, in explaining this sudden acceleration of the universe, that about 4 to 5 billion years ago, and as I said, imagine that this takeoff is put here in the past by about 4 to 5 billion years ago, that at that time, the distances between the galaxies became sufficiently large so that the cosmological constant started to dominate over gravitational attraction, right? If 2 objects are distant enough, then the force of gravity between them, the force of gravitational attraction, would be reduced. And the cosmological constant, that force that is pulling them apart, does not depend on the distance. So 4 to 5 billion years ago, the universe became sufficiently large so that the cosmological constant started to dominate over gravitational attraction. Okay? So at that time in the past, lambda, this is capital Greek letter lambda, corresponding to L in other alphabets, started to dominate over gravitational attraction, and the expansion started to accelerate. Okay? So this is the way how we now deal with this observation that the expansion of the universe started to accelerate few billion years in the past. So of course, a natural question is, what is it? Right? We can understand mass, matter, right? We represent ordinary matter. We can also perhaps deal with the dark matter, right? We don't know still what it is, but based on how the stars at the edge of a galaxy move, they move too fast, or how the galaxies in a galaxy cluster move, they again move too fast. We know that there is some other stuff that we can't see that interacts weakly with ordinary matter. It interacts with ordinary matter via force of gravity, right? So that's how we know it's there. But it's still something that, it's perhaps we could understand. But what is cosmological constant? And there are several guesses, which I don't want to discuss because it would be meaningless. I would have to teach you a little bit about quantum mechanics and to explain one way of how people approach the nature of cosmological constant. But I think that honest answer is that nobody knows. Okay? So whatever it is, we call it dark energy. Okay? So we have ordinary matter or baryonic matter, the stuff we are made of, and stars and galaxies and so on and so forth. We also have dark matter, but we have this new thing called dark energy. All we know about its properties, it has to have a positive energy density. Amount of energy per unit volume of space has to be positive. But it also has to have a negative pressure. Okay? And what is a negative pressure? Well, I tried to illustrate that here. I could make my own drawing for a positive pressure. It was easy enough. So imagine you have a vessel of some sort, right? You fill it up with liquid, and you drill a hole on the side. What happens, of course, is that the liquid will start to come out. Why? Because the liquid exerts positive pressures on the walls of the vessel, right? So unless I oppose this pressure from this side, the positive pressure, by pressing in the opposite direction on the hole, the liquid will come out, right? I have to stop it. So this is, and most of the things we are familiar with, like the pressure of the air in your tires is also positive, right? It pushes on the side. If it's not high enough, every tire leaks. You have to pump enough so that your wheels would function properly. So this is positive pressure. The negative pressure is realized in a stretched rubber band, right? When you stretch a rubber band, right, you now have to pull in the opposite direction. Here you have to push, right, into the positive pressure. Now you have to pull in the opposite direction. Why? Because now the pressure in the band acts this way. It tries to contract it. In the case of a fluid, a gas or a liquid, it expands under its own pressure. Here, the negative pressure would cause the rubber band to contract. Okay, so all we know that whatever it is, dark energy has to have positive energy density, and it has to have this negative pressure. So the question is, what is the total omega of the universe? Remember, the parameter omega determines, among other things, the curvature of the universe. And it turns out that observations show that the contribution from ordinary matter and dark matter to omega is about 0.3. And that observation was there up until late 90s, when it was discovered that the expansion of the universe is accelerating. So you can ask the question, how do we know? How do we know what is the contribution to omega from ordinary matter and dark matter? Well, you can take a large assembly of galaxies, do statistics, count the number of stars, how many stars on average they contain, the size of the star, how much mass they contain, and from that you can get an inference as to what contribution of ordinary matter to omega is. You can do something similar to the dark matter. It's more complicated. You can take many galaxy clusters, and then from the way the galaxies in the cluster move, you can estimate how much dark matter has to be in a galaxy cluster, and then you do again statistics over very many such clusters and estimate the contribution of dark matter to omega. And it turned out that, and it's still correct, roughly, that the total contribution of ordinary matter and dark matter to omega is about 0.3. And that was never very satisfactory. And I'll tell you why, without going into the details. It turns out that general theory of relativity predicts that if omega was less than 1, if it was, say, 0.3, that it would very quickly become 0. The same if it was bigger than 1. There were theoretical reasons, deep theoretical reasons, why omega should be exactly equal to 1. Okay? And then when it was discovered that the expansion of the universe is accelerating, then they realized that there should be contribution to omega also from dark energy. And its value is then deduced based on the rate of the expansion of the universe, or the rate at which, or the acceleration in the rate of the universe. And it was estimated that the contribution of dark energy to overall omega is about 0.7. So that the total value of omega is 1. Now, I mentioned the last time that there were 3 satellite missions that examined, you can tell exactly from inhomogeneities in microwave background, the different components, the ordinary matter, dark matter, and dark energy are responsible for these inhomogeneities. And by doing the statistics on these things, you can then calculate, it's a complicated procedure, you can calculate the percentages of different components of the universe. And the latest mission was just finished. People are still analyzing data by this probe Planck, named after Max Planck, who was one of the founders of quantum mechanics early in the 20th century. It's an effort largely launched by Europeans. Before that, there were 2. There was COBE and WMAP, right? And before Planck, the distribution of different components of the universe was estimated to be like this. Ordinary matter, 4.5%, dark matter, just under 23%, and dark energy, about 73%. After more detailed, more precise measurements done by Planck, these numbers have been revised. There's now, we know there's a little bit less of that dark energy compared to what we thought before, but it's still close to 70%, right? So these numbers that I give here, they are just approximate values of what has been deduced, right? But we can round all these numbers to about 70%. Okay, there is a little bit more of dark matter than thought before, right? Now it's almost 27%. And there is a little bit more of ordinary or baryonic matter than what thought before. Okay, but nevertheless, it's still roughly a dark matter and ordinary matter is about 30%, 0.3, and dark energy is about 70%, 0.7. Okay. Now, when you think about it, we really understand very little about the universe. We don't understand what 95% of the universe is, because we don't know what dark matter is. We don't know what dark energy is. Okay? We just know that they are there, dark matter, to explain the speed of the stars at the edge of a galaxy, or the speed of galaxies in a galaxy cluster. We also know that we have to have this dark energy to account for accelerated expansion of the universe, but we don't know what either one of these are. We understand only this relatively small wedge of the total composition of the universe, right? So there's, you know, when people say, oh, you know, we are just around the corner to understand everything, that is not the case. There is so much that we still need to find out, and I find that extremely exciting, right? It's extremely exciting. One thing that perhaps you are wondering about, and you can say, okay, if the universe is expanding, because space and time are expanding, how come the time not expanding now? How come the time not blowing up if everything else is expanding? Why is the sun not expanding, right? Well, it turns out that what is holding me together, or what is holding the sun together, are ultimately the forces of electrostatic attraction between different parts of atoms in my body. It's that force of electrical attraction that is actually holding me together to occupy this same volume, unless, of course, I start overeating, right? Then I would expand, right? So the space itself is expanding, but different objects in it, like, you know, people, Earth, stars, they are not, because they are held together by different concrete forces that resist that expansion, right? So the space is expanding around us, but objects like myself, like the Earth, like the sun, they keep more or less the same volume.